topic is on stoichiometry. Stoichiometry is a concept whereby it relates the amounts of reactants with the amounts of the products in a chemical equation. So, for example, if I gave you this equation whereby we have acetylene, C2H2, and we're reacting it with oxygen, and we're going to produce CO2 plus H2O. In other words, we're going to have carbon dioxide and water vapor. If I were to give you that equation, you would automatically think to yourself, you need to balance this equation. And of course, you'd then put a 2 here, and then we would balance it out. And I'll save you some time, and I'll do it for you. We're going to 2 here, 5 here. We need 4 carbon dioxides and 2 waters. So you balance the equation, but up until now, there's really been no purpose to balancing the equation. But now with stoichiometry, we're going to find out the purpose of this. So you'll notice that with our coefficients here, first of all, we've got 2 and 5. We have two acetylenes and 5 oxygens. What those coefficients really relate is the number of moles of each. So if I had, for example, 2 moles of, let's say, acetylene, then I would need 5 moles of oxygen to react with it. Additionally, 4 moles of carbon dioxide would then be produced along with 2 moles of water. Notice that we have then 2 moles of acetylene are needed to react with 5 moles of oxygen here. And so the reactants, we have 7 moles of reactants, but we're only going to produce 6 moles of products. And that's often the case. The moles of the reactants don't necessarily add up to the moles of the products. But these mole ratios then come into play when we're doing calculations to determine the amounts of each needed. So for example, I'm going to start with what's called a mole-to-mole calculation. This is the simplest of the stoichiometric problems. And a question might read, how many moles of acetylene, let's just go C2H2, are needed to react with, let's go with 1.579 moles of oxygen. Okay, so let's say we start with that. Well, now we're going to use those mole ratios to do the calculation. So in this case, I'm going to have 1.579 moles oxygen. And I'm going to use these mole relationships to get my answer. So I know since that we're just going to use unit multipliers to do our calculations. So if we have moles of oxygen in the numerator here, of course, then we're going to need moles of oxygen in the denominator. And we're trying to determine the moles of acetylene. So we're trying to get to moles of acetylene. So then I'm going to put moles of acetylene in the numerator. And there's going to be a number, of course, that's going to go in front here. And that number is just the coefficients that are in front of the substances. So we have a 5 up here for moles of oxygen and a 2 for the moles of acetylene. So it's going to be for every 5 moles of oxygen, 2 moles of acetylene will be required. And so we're done right here. That's all we had to do for our calculation. We punch it in our calculators. So we have 1.579 and times 2. And divided by 5, and I get 0.6316 for my answer in moles of C2H2 acetylene. And significant figures, here we have 4 significant figures in this one. Here we have infinite number of significant figures since it's an exact relationship. So we get to keep 4. So our answer is 0.6316, our final answer. So that would be a mole-to-mole calculation for that. Now, the same thing can be done with the products. The coefficients in front of the products would react the same way or be involved in the same way as we just did with the reactants. So, for example, I'm going to take, the question might read, calculate the moles of water produced when, let's go with 8.55 moles of acetylene react. So again, I'm going to start with what's given. So what we're given here is our 8.55 moles of C2H2, excuse me, and using unit multipliers, I'm going to put moles of C2H2 in the denominator right away because those have to cancel out. And we're trying to get to moles of water, so moles of H2O up here. And then I go back to my original chemical equation to determine the numbers that are going to go in front of those moles. So go back to the original equation, and we know that for every 2 moles of acetylene, it will produce 2 moles of water. So it's a 2 to 2, or in other words, a 1 to 1 relationship. Well, I'll just put in 2 so that you understand where it's coming from. So we have 2 moles of water to every 2 moles of acetylene. And so, of course, when we do the calculation, we obviously don't have to punch that in our calculators, I hope. And so we have 8.55 moles of water will then be produced. So it's as simple as that. So again, that was the simplest of all the stoichiometric problems right there, the mole-to-mole calculation. Now, in a laboratory setting, of course, we aren't going to be using moles, we're going to be using grams. And so what we need to do is relate the masses of the reactants with the masses of the products. So we could do what's called then, let's just take it the next step. Let's say we go from moles to mass. So we're going to do a calculation involving all these. So it might look something like this. The problem might read, calculate the mass of carbon dioxide produced when, let's go with 0.0557 moles. Moles of, let's go with oxygen react. So again, I'm going to start with what's given here. So I always start with what's given. And here I have my 0.0557 moles of oxygen. And again, using unit multipliers here, we'd have moles of oxygen in the denominator. And we're going to go to moles of CO2. Going back to our original reaction to figure out those coefficients, okay, so look at the coefficients to figure out what values are going to go in here. So I go back to my original equation, and I know that for every 5 moles of oxygen, I will produce 4 moles of carbon dioxide. So it's a 5 to 4 relationship there. So go back to our original equation, or our calculations, and we said 5 moles of oxygen, 4 moles of CO2. But they're asking for the grams of CO2, in this case, not for the moles of CO2. So we have to take it one step further. So we know then Well, we know how to go from moles of CO2 to grams of CO2. And that we've learned how to do already. And what we need to do is figure out the molar mass of CO2. Again, just a refresher on molar mass. I've got one carbon here, and I've got 2 oxygens, and the mass of carbon is 12.01. Mass of oxygen is 16.00. So here we'll have 12.01. Here we'll have 32.00. And we add them up, and we get our 44.01 grams per mole. Okay, so there's the molar mass of carbon dioxide. So for every 1 mole of CO2, we're going to require, or we will produce 44.01 grams of CO2. So now we just have to punch that in our calculators and we get our answer. So here we have 0.0557 times 4 divided by 5 and multiply that by 44.01. And we get 1.96. It's kind of a big number here. We're going to get 1.9610856. Okay, that would be grams. Now, significant figures, again, going back to that. Here we have 3 significant figures. Here we have an infinite number of significant figures because it's against an exact relationship. And from the masses that we use, we have 4 significant figures here. So we have a maximum of 3. So we can only keep 3 of these digits. And so what we end up with in our final answer would be 1.96 grams of CO2. Okay, there's our final answer here. So that's a mole-to-mole to mass problem. Now we could have mass on the front end. So starting again, problem might look like this. The question might be, or it might involve a mass to mole. That's what this one is. How many moles of CO2 are produced when, let's go with 64.00 grams of CO2, or excuse me, of oxygen react. So in this particular problem, again, we start with what's given here. We have 64.00 grams of O2, so that's what I start with, 64.00 grams of oxygen. And in this case, we are going to convert right away to moles of oxygen, because again, when we're going to end up using our balanced chemical equation, and those coefficients in the balanced chemical equation relate the mole-to-mole ratio, not the grams. So I have to get my moles into grams. Excuse me, my grams into moles. So I have oxygen, which is a diatomic. So this is going to be 32.00 grams of O2 is going to be 1 mole of O2. Now notice I doubled the mass of my oxygen. Okay, so oxygen has a mass of 16, but because it's a diatomic in this particular case, it's going to be doubled. So now I have moles of oxygen. So now I can use my balanced chemical equation. And I know from before, now again, we're going from moles of oxygen here to moles of CO2. So we use our balanced chemical equation from before, all right, which shows that the relationship is going to be 5 to 4. So for every 5 moles of O2, it's going to require or produce 4 moles of CO2. And again, we do it, punch this in our calculators. And, you know, maybe you have you can see that 32 goes into 64 twice. Okay. And so we know that goes in there twice. And really, we're going to have 4 times 2 is 16 divided by 5. So our final answer here should be 3.2 2 moles. Now, what about significant figures? We got to be careful with this one because we might have to add some zeros here. You can see that the 64.00 has 4 significant figures. This too has 4 significant figures, and this would be an infinite number of significant figures because it's an exact relationship. So we have to keep 4 significant figures. So we can't leave our answer as 3.2. We would put 3.2, and then we have to add a couple of zeros here, and that would be moles of CO2 as our final answer. Now, we've done a mole-to-mole problem. Okay, so originally we did a mole-to-mole problem before. Okay, that was the simplest one. And then we proceeded to go to a mole-to-mole-to-mass. And then we just finished with a mass to mole problem. And now the last type, and you're probably going to guess already, but it's going to be a mass to mole to mass calculation. So the question might read, determine the mass of water produced when, let's go with 81.5 grams of carbon dioxide are produced. So in this particular case, again, we're starting off in grams, and we have to end in grams. So I have my 81.5 grams of CO2. That's what I start with, and we need to get that into moles. Again, because going back to the balanced chemical equation, those coefficients relate the mole-to-mole relationship, not the grams. So I have to get the CO2 into moles. So I know that 44.01 grams of CO2, we did the molar mass calculation before, that's 1 mole of CO2. So I have that in moles. And then for every, going again to the balanced chemical equation, we have here for every 4 moles of CO2, there's going to be 2 moles of water that's going to be produced with it. So this is going to be 4 moles CO2, and it's going to relate to 2 moles of H2O. But the question is asking for mass. It doesn't state it, but we'll just assume it means grams. And so then we're going to go for moles of H2O, 2 grams of H2O. So we have to calculate the molar mass of water, which I'm going to just save you some time. It's 18.0. 2 grams of H2O is 1 mole of water. And we just punch that in our calculators to see what we get for an answer here. So 81.5 and I'm getting the answer of 16.685185, etc., etc., etc. Okay, significant figures. Here we have 3. Here we have 4. Again, infinite and 4. And we can only keep 3 significant figures. So we can see then that we're going to be rounding this 16.7 grams of H2O will then be produced. Oops. And that is stoichiometry in a nutshell.